Good morning, everyone. Welcome to Software Engineering. I'm Zhang Shuang from Software College, Northeastern University. Today, we are going to learn object-oriented analysis, class modeling. What is a class diagram? A class diagram shows the existence of classes and their relationships in the logical design of a system. A class diagram may represent all or part of the class structure of a system. Class diagrams show the static structure of the module. In particular, the things that exist, such as classes, their internal structure, and their relationships to other classes. Class diagram is a static view of a software system. Primarily supports the functional requirements of a system. Actually, to achieve a class diagram, the designers or the analyst should extract the classes and their attributes, and to represent them using an entity relationship-like diagram. So where does the classes come from? Actually, the classes are deduced from use cases that we have achieved during the phase of use case modeling. So now you understand that the first step of OA should be use case modeling. And then once we achieve the use case diagrams, we can do class modeling, right? Actually, there are two approaches to class modeling. Approach 1, non-extraction, and approach 2, CRC, class responsibility collaboration. Non-extraction always works, so it is used the most often. But CRC needs to have domain expertise. Well, CRC class is very good for testing class diagrams. That means it's a wonderful testing approach. Your students are required to master skill for non-extraction to get class diagrams. So how to do non-extraction for class modeling? Step 1, concise problem definition. That means to define product briefly and concisely. Let's say the elevator problem. Since all of us have used elevator quite often, and I'm sure that every one of us can describe the business flow of the elevator quite well, but I'm afraid that each person, different person will give a different description for it. Well, to extract noun from the business logic, the first thing that we should do is to define the product briefly and concisely. So the elevator problem will be described in this way. Let's read it together. Buttons in elevator and on the floor control movement of n elevators in a building with m floors. Buttons illuminate when pressed to require the elevator to stop at a specific floor. Illumination is cancelled when the request has been satisfied. When an elevator has no requests, it remains at its current floor with its door closed. So you can see that the business flow of elevator problem is described really briefly and concisely. So from this description, we can extract some nouns from it. So that means formalize the strategy. Identify nouns in informal strategy. Use nouns as candidate classes. So we get all the nouns from the description, including button, elevator, floor, movement, building, illumination, and door. Okay, so totally 7 nouns. So let's analyze them one by one. Movement and illumination. Actually, movement and illumination are just abstract nouns. They may become attributes of some other entities or nouns, but they cannot become classes by themselves. So that means they are excluded from our target system. Floor, building, and door. Actually, the problem that we are trying to solve and discussing is elevator and floor, building, and door are outside our problem boundary. So they are also excluded. So now we get only two nouns left, elevator and button. And they can become the candidate classes. And we also find that actually buttons can be divided into elevator button and floor button. That means the button inside the elevator and the buttons on each floor. So far we get four nouns, four candidate classes. So we'll achieve the diagram for elevator, the class diagram, like this. Button. Button has attributes illuminated. The data type for illuminated is Boolean, so that means it's true or false, on or off. And elevator button and floor button are derived classes of button. Elevator. Elevator has attributes of doors open or not. So its data type is also Boolean. Within one elevator, there are M elevator buttons because there are M floors, right? Each elevator button to indicate one floor, right? So the relationship between elevator and elevator button is communicates with. So that means they communicate with each other between elevator and elevator button. Okay, elevator button, elevator and floor button. Totally there are N elevators, and totally there are 2 times M minus 2 floor buttons. We know that there are M floors, and there are 2 buttons on each floor, one for up and the other for down. So that means 2 times M, but Y minus. Because the first floor and the highest floor has only one floor button, right? Okay. Only up button is needed for the first floor and only the down button for the highest floor. So that's why 2 times M minus 2. Okay. And these N elevators will communicate with the floor buttons on each floor. So their relationship is also communicates with each other. Maybe you will think that buttons do not communicate directly with elevators. Actually, that's true. So we need an additional class, elevator controller. Basically, the buttons and the elevator will communicate with the elevator controller rather than communicate with each other directly. Okay. So the diagram will be like this. One elevator system, one elevator controller. So this elevator controller will control N elevators. And it also controls 2 times M minus 2 floor buttons. It controls M times N elevator buttons. Okay, so this the second iteration of class diagrams for elevator system. Okay, so let's discuss some other systems, other cases. Let's say university system. So for example, Northeastern University. The university is a whole class, and it is composed of more than 1 colleges. There are software college, art college, foreign language college, and so on. And each college is aggregated with teachers and students. And the students will take course, and teachers will instruct some course. Never forget the multiplicity. So this is the example for university system. Next case, bank system. Well, I would like to describe the bank system in this way. A bank system has customers who open accounts. A customer can hold accounts in a bank. He can deposit funds to accounts, can withdraw funds from accounts, and can also transfer funds from one account to another. A customer can check balance of his own accounts and transactions records, including depositing, withdrawing, and transferring. Okay, so this is just the exact what we have interacted with bank system, right? So the class diagram for it will be like this. The bank itself is a class, an entity class, and surely the bank has more than one customers. And the bank also has more than one account, and the customers may hold some account, and one account can be held by some customers, and each account some transactions such as deposit, withdrawal, and transfer. Well, the multiplicity for deposit, withdrawal, and transfer may be 0 to more. Okay, so this is a diagram for bank system. Actually, here we get something to explain about the classes in this class diagram. Deposit, withdrawal, and transfer are verbs. Actually, we have said noun extraction, so that means we should take some nouns as classes. But why in this diagram we take some verbs as classes? Well, the reason is that even though there are some verbs, they have some attributes. That's the most important. Let's say for deposit, surely it should have attributes such as account number, deposit date, funds, okay, or currency, and so on, right? So surely deposit should become a class. So this is the class diagram for bank system. Case 3, online shop. This is also something that we are quite familiar with, since almost all of us have bought something from some e-shop system. All of us are customers, right? And each customer should have its own user ID and password, his own account or balance, and so on. And on the online shop, the customer can browse the product. Let's say if we want to buy some books from the online shop, and then you will browse the products, okay? And each product has its own product ID, product name, product description, unit price, unit weight, picture URL, and so on. And what's more, the customer should be able to place orders on the system. For each order, there should be such attributes: order ID, user ID, order date, cost of items, total weight, shipping preference, shipping cost, total cost, and so on. Okay, and we understand that we can order multiple products in one order, right? Okay, so that part is called order item. So in each order, it can have more than one order items, and each order item should be indicated with product ID and the quantity and cost. So this order is really something just like we bought something from supermarket, and for each shopping you can buy multiple products. The class product will describe each order item. So this is a diagram for online shop. Well, surely the class diagrams that we went through just now are quite small. Actually, we didn't include all the business logic inside because the limitation of space of the slide. And surely for a real project, let's say the middle-sized project or a large-sized project, there will be many classes, right? And then you can assume that the class diagram will be very big. And then you may think that, is there a better way to organize class diagrams? Of course, the answer is yes. The solution is package. Package is a general purpose machinism for organizing elements into groups, and a module element that can contain other module elements. Actually, package is not something new for you maybe, because you have learned package in Java. How to design or how to organize packages. The rules for packaging is that Classes with aggregation or composition belong to the same package. And classes with a lot of association belong to the same package too. So that means the classes who communicate or interact with each other closely should belong to the same package for convenience and performance of codes, right? Okay, and surely a package can include other packages. It is quite similar to folder in operating system. For example, in Java class library, let's say class file is in package IO, and the package IO is in package Java. So the full name of file is java.io.file. You must understand that too deep nested package is not a good idea. So what we should do is that to avoid too deep nested package, and normally 2 to 3 layers is okay. Okay, so these are the notation for package. So this package is named server, and this package is named GUI. And inside this package, there are some classes. Let's say class 1, 2, 3, 4, and so on. And in GUI package, there are some classes like a window frame, event handler, and so on, right? Okay, so you see that in this way, classes are organized nicely and reasonably. Next, CRC cards. The first C means class, and the R means responsibility, and the last C means collaboration. You see that CRC means the responsibility of the class and its cooperation with the other classes. CRC card is used since 1989 for object-oriented analysis. So that means for each class, the analyst will fill in cards showing the name of the class and its functionalities, also called its responsibility for R. And the list of classes it invokes, that means collaboration classes. Okay, so then you see we get CRC. The strength of CRC cards is that it is a powerful tool for highlighting missing or incorrect items. So just like what we have introduced just now, is that CRC cards is a wonderful tool for testing OA results. But its weakness is that domain expertise is needed. So that means for object-oriented analysis, CRC cards are not an approach that can be mastered and used by anyone. So much for class modeling. Thank you.